Good afternoon, and welcome to our Friday afternoon briefing here at the 229th meeting of the American Astronomical Society at the Gaylord Texan here in beautiful, snowy Grapevine, Texas. I'm Rick Fienberg. I'm the AAS press officer, and I'm assisted today by my two deputies, Inga Heyer, who is monitoring our webcast for off-site journalists, and Larry Marshall, who will be manning the microphone for the question and answer period. Please remember to silence your cell phones, pagers, beepers, etc. And if you're on the AAS press list, you're going to receive two press releases. They'll be in your inbox when you get back from the briefing. There may be one or two more coming, but don't panic if you only find two. The way briefings work here, in case this is your first, is that I will introduce the panel. They'll then give their presentations one after the other, from left to right, though they'll come up here to do it. And then we'll have the questions at the end. We'll take questions from here in the room, and then we'll go to the webcast. So in the good old days of the AAS, not that long ago really, every meeting was guaranteed to have at least one, maybe two press conferences on black holes. Black holes have now given way to exoplanets. Every meeting has at least one, sometimes two, press conferences on exoplanets. Today, it's not just exoplanets, but it's also exocomets. These, of course, are planets, comets, etc., circling stars other than our sun, one of the hottest areas in astronomy today. Every time I see a junior member of the AAS and I ask them what they're studying, they always say exoplanets, as if there's nothing else out there. So we're going to hear 4 presentations from 5 speakers. First will be Eden Girma from Harvard College. She's going to tell us that our galaxy's black hole is spewing out planet-sized spitballs. Then James Vesper from New Mexico State University is going to consider rogue planet encounters with the solar system and ask, and perhaps answer the question, is Planet 9 a captured rogue? Then we have a tag team, as we've had at least once before at this meeting. Thayne Currie from the Subaru telescope at the National Astronomical Observatory of Japan and Tyler Groff from Princeton University are going to team up to tell us about first light results from Maunakea's new dedicated Exoplanet direct imaging system. And bringing up the rear, last but not least, Carol Grady from Eureka Scientific will tell us about new Hubble observations of transiting exocomets around a white-hot southern star. So with that, I'll turn it over to Eden, and we'll get started.
Great. Thank you, Rick, and thank you all for being here. I'm really excited to share with you the work that I've been developing along with Dr. James Guichon on this project. So just to sort of set the stage of what this is all about, I'm going to explain briefly what tidal disruptions are. You can think of them as a 3-step process between a black hole, a supermassive black hole, in this case Sagittarius A star, and a star that passes nearby. So first, we have the star that passes so close to the black hole that it reaches a distance known as the tidal radius, where the tidal force of the black hole overpowers the self-gravity that's keeping it together. Once it reaches this distance, the star then experiences the distortion due to those tidal forces, and then is spaghettified into a long stream of stellar mass. So this is the normal paradigm. However, recently, other researchers have shown in more in-depth hydrodynamical simulations of this process that around the 2-year mark, there's actually enough residual self-gravity within the stream for it to collapse into these Jupiter-sized fragments. And these fragments are then being shot back out into the galaxy at speeds ranging between 1,000 kilometers per second to even 10,000. So the natural question is, okay, if these are being created, where do they end up? Do they end up near us? So our projects sought to answer those questions. And we answered this question by creating a code that would be able to simulate the fragmentation formation process and then plot the spatial evolution of these fragments throughout Hubble time. So there are two components to this code. First was a part in Python, which initialized everything, which randomly drew a tidal disruption, and from there calculated the number of fragments in this tidal disruption along with their initial conditions. And then the second part was conducted in Mathematica, which did the hard work of integrating, of solving the second differential, force equals mass times acceleration equations, and basically solving them for each time step. And as you see in this video, which I'll play again, basically just shooting out these particles, solving their evolution of their position up until the maximum time. So here you see we simulated 50 tidal disruptions and integrated over 10 to the 10 years. This video specifically just shows 10 to the 7 years, and you can see all the fragments, how they spew out really, really beautifully in those streams. So the results of these simulations showed that actually a vast majority of our fragments completely escaped the galaxy. We were able to characterize which ones were bound versus which ones were unbound to the galaxy by incorporating that criteria within our integrator. And in fact, 95% of fragments were characterized as unbound. They completely escaped the galaxy, whereas only 5% are characterized as bound. Looking into the bound fragments, and you see this histogram, which shows on the x-axis sort of the farthest distance that these fragments travel in their orbit, along with the probability on the y. We see that 90% of the bound fragments only get as far as 100 parsecs away from the galactic center. And for reference, our sun is 8 kiloparsecs away from the galactic center. So a lot of them, if they're at all bound, they're most likely to be very tightly bound orbits around the black hole. Whereas for the unbound fragments, we found that the majority of them were deposited within the range of 10 megaparsecs to 100 megaparsecs. And an additional question that we wanted to answer, again, was, all right, if these fragments are being produced, how close is the nearest one to our sun? And you can think of answering this process sort of through a process of filtering. If you know that all of these fragments are being spewed out, a fraction of them have to end up in some way 8 kiloparsecs away from the galactic center. And then out of those fragments, you can think, all right, if I am at the sun and if I identify a surveying radius r, I can also identify the fraction of these fragments that end up within sort of my surveying sphere, which this equation summarizes. So to answer our question, okay, what's the distance to the nearest fragment? We need to figure out, all right, if I want to view at least one fragment, how far would I have to survey? And this number turns out to be around 200 parsecs, which for reference is about 700 light years away from us. So to summarize sort of the new insights that we've gained from this work, is that a majority of the fragments produced in these tidal disruptions are more likely to be unbound to the black hole and traveling extremely, extremely fast. Those which are bound that are produced are more likely to be tightly bound to the galactic center. However, the nearest fragments, because of the rate of occurrence of tidal disruption events, we know that so many of these fragments are being produced that the nearest fragment might be as close to us as 700 light years. There are a lot of questions that then come up, one of them being, all right, well, how can we find these fragments if they exist, and what would they look like? So first you have to think that, all right, these fragments are produced from collapsed stars and have no source of internal energy. So as they travel, they're getting colder, and by the time they reach us, they'll be extremely cold. So while we can see them in the infrared, they're not necessarily visible in the optical. They might be able to be directly detected by very, very large telescopes such as the James Webb, but we're not sure. Something that may be more likely is using microlensing because these objects are moving so quickly, over 10 times the speed of normal free-floating planets. They might be more detectable. And additionally, another question that we want to ask is just, what about tidal disruptions in other galaxies? So Yes, so this is the work, and just briefly, I wanted to acknowledge these people. Thank you for their help in all of this, and thank you all for being here, and I look forward to answering any questions you may have.
Hello, I am James Vesper. I'm an undergraduate from NMSU under Paul Mason, and I'm studying the effects of rogue planets on already created the star systems. So a rogue planet, or also known as a free-floating planet, we found that they may be more abundant in the galaxy than we originally thought. In being more abundant than stars in the solar system. So with my experiment, I performed 156 different experiments with a whole range of masses ranging from super Earths all the way up to super Jupiters, and also the different entry angles that they have coming into our solar system. So from this experiment, I found that they roughly do two different types of things. That's going to be they're either slingshotted further out into the galaxy, or they are captured by our solar system. I use our solar system as my basis for the experiments. So from those, I found roughly 60% of all the encounters were slingshotted into the galaxy. As I'm showing here. The slingshot will come in real close to the sun and then be shot back out into it. And what that was in the case for, like I said, 50% of them. So it was just the rogue comes in, rogue goes out. In 10% of those encounters, though, it will take one or more planets with it. So in effect, creating even more rogues in the universe. So with this here, this is an example of a capture. That is where the rogue body comes in and it's captured by the sun, but it doesn't disrupt any of the solar orbits that we already have. This is an exchange here. What this means is that the rogue comes in and it knocks one planet out, keeping the same amount of rogues in the system, but now we have a new planet out there, as you can see, going through Uranus's orbit. Next, I have here this is a kick and stay. This is probably one of the more extreme ones that I was talking about for the slingshot effects. Not for the slingshots, for the capture effects. What it does is it comes in and it will actually knock out multiple planets. As you can see on the right slide there, that one is shown that all of the outer planets have been knocked out and the inner planets have remained in, but their orbits have been very stretched out. On the left-hand side there, I have the worst-case scenario where every planet in the solar system has been knocked out completely and is now a rogue planet. So this brings me to the question, is Planet 9 captured rogue? While initially that wasn't what I was looking for, based on a lot of the information, I find that it could be plausible because of the entry grades coming in, regardless of whether it's prograde or retrograde with it. So a lot of the things that were brought up, that obviously those very large planets that I was talking about coming through can result in total system destruction or just the changing of the orbital pathways that we already have. However, the smaller ones, that are about Earth-Neptune size, they usually get kind of just chucked right back out into the galaxy there, with having little to no effect on it. Seeing the orbits that have come in as such, as I said, it is very plausible that in a soft capture type scenario, the Planet 9 might be able to exist out there as I predicted with some of my data. However, the more common result is that the rogues that come through are going to just simply create more rogues rather than be captured by the systems. Our solar system, just based on how our inner system works with it, it's pretty obvious that we have not had an encounter with anything Neptune-sized or larger at this point in time, just because of how tightly packed they are in the orbital system that we have established already. So, thank you very much.
All right, can everybody hear me? Okay. So for thousands upon thousands of years, we've looked up at the sky and only known about the planets in our own solar system. It was only 8 years ago that we first saw a planet around another star. And that was done from Maunakea with a typical facility AO system, kind of a workhorse system for wide use of scientific purposes. So today I want to talk to you, and Tyler would like to talk to you about first light results from Maunakea's first dedicated exoplanet imaging system, the Subaru Chronographic Extreme Adaptive Optics project. So to give you a sense of context, in the last 15 years, we've seen an explosion in the number of extrasolar planets detected. This is one example from the Kepler mission, or even see planets roughly the size of Earth at astrophysically interesting locations in terms of their habitability. But I think ultimately what I want, and what a lot of people want, is something like this, where we actually see these planets, where we see that pale blue dot, and when you get wavelength information that can tell us whether or not that planet has oxygen and other molecules in its atmosphere. And we're taking first key steps to be able to establish this right now from space with NASA missions, and then also from the ground with projects like SkexAO. So what is it? It's an extreme AO imager for Subaru focused on imaging planets that are very faint and located very close to their host stars. It allows us to rapidly correct for blurring induced by the atmosphere due to turbulence, and get very, very sharp images. And so the middle panel shows what happens when we turn SkexAO on. You get that bright stellar halo, that glare that is preventing us from imaging planets starts to collapse, and we can see intrinsically fainter and fainter objects. It's coupled with science instruments. I will be talking about the results from the planet imager, the high-chow camera. Tyler will be talking about results from planet spectroscopy with the Charis integral field spectrograph. Then I'll wrap up a little bit describing the future trajectory of this project. This is our first image that we are working on of an extrasolar planetary system with SkexAO. We detect 4 planets orbiting HR 8799. This is the first planetary system ever imaged. If we compared that image to comparable images in terms of the depth from a facility AO system also on Maunakea, we're able to see an additional planet. We're able to detect all 4 planets at a much higher signal to noise. We effectively only flipped the on switch for this system in the last couple of months, and it took very little time to discover our first object. This is a planet-forming debris disk around a nearby star, HD 36546, which is actually in the constellation Taurus, so you can probably see it tonight if you look up and have some binoculars. This is really interesting because this may be the youngest debris disk, the youngest system around which protoplanetary disk gas has gone, and we're actually seeing like sort of proto-Kuiper belt forming, maybe the youngest one we've ever imaged. So now I'll move to have Tyler talk about results from the Charis integral field spectrograph.
Thanks, Thayne. So Thayne just talked about the imaging capabilities that exist with SkexAO, and what I'm going to talk about is the next generation spectrograph that's going along, that's sitting right next to this imager now. And it's called the Charis integral field spectrograph. Charis has a 2 by 2 arc-second field of view, so it's actually even smaller than high-chow. The main point here is that we are optimizing this system for low inner working angle. We're really looking forward to these future extremely large telescope applications where the discovery space is going to get pushed by moving to inner working angle. And when we built Charis and designed it, the entire purpose is to optimize the spectrograph so that it can work with SkexAO and really achieve that low inner working angle. And to that end, we have 4 imaging modes in Charis. There is a high resolution mode, as we call it, which is about an R of 70 in J, H, and K bands for your conventional thermal imaging and characterization. What we added was this low resolution mode, which actually spans the entire bandpass from 1 to 2.5 microns. And just to give you an idea of the difference of those two things in the spectrum, on the lower right graphic, you can see the low resolution and the high resolution thermal background from the spectrograph. That's the exact same spectrum in both K and low resolution modes. So it just gives you an idea of the extreme bandpass that we have in that low resolution mode. And the entire purpose is so that we can actually do spectral subtraction more effectively and push the inner working angle of that spectral post-processing that we're allowed to do. And that's, again, to push the inner working angle with SCEX-AO, and as you're going to see in a moment, that's actually working incredibly well. In the future, we're going to be adding a PDI mode because that was one of the most impressive bits of the seed survey. And so I'll just move on to that. To give you an idea of what this is, or what we get out of Charis and SCEX-AO combined, I have images of HD 32297 and HR 8799. Charis only saw 3 of HR 8799 planets, but it's B that we're missing. The planets that you're seeing there in that middle top pane is C, D, and E, which have signal-to-noise ratio detections of greater than 15. The left pane, for reference, is just an ADI subtraction that Tim Brandt did for this image. In that ADI mode, we don't see E. When we add the broadband capabilities of Charis and actually do spectral subtraction, we get just an amazing and wonderful detection of E. And the spectrum that we extract from those 3 planets are shown in the bottom panes. And they're preliminary. We just started engineering runs in July, so this is extremely encouraging. And HD 32297 is actually data that we just took about 2.5 weeks ago. So this is extremely recent, extremely encouraging. And everyone, the PI, instrument PI Jeremy Kasdan and Masahiko Hayashi, the PI of the MEXT grant from NAOJ that funded Charis, are extremely excited by this, as is Jeff Chilcote, who is my partner on these observations. So the SCEX-AO team in general is extremely happy with this, and I'll add that we didn't have time to put in the newest results for the extreme AO, but Olivia Guiana is doing a fantastic job with that in the SCEX-AO team. We had 10-minute spans of data where the PSF didn't change at all. And that's not what this data is from. So I think you can expect to see even better results coming from this in the future. We're very excited about it.
So where are we going with this? I want to chart the path forward with SCEX-AO to close. So we have contrast curves typically like this in bad conditions. The kinds of planets that we want to image, the solar system analogs around a sun-like star, are very, very difficult. They're outside of the reach of what we can do from the ground. But if we try to image these planets around low-mass stars, the reflected light contrast can start to climb. So for example, the habitable zone for an Earth in Earth is only order of about 10 to the minus 8, or a little bit better in terms of contrast versus 10 to the minus 10. So in the next couple of years, we're going to gradually see the gap between the kind of planet imaging capabilities we have and the abilities we need to image an Earth collapse. And this will especially be true if we put SCEX-AO on a 30-meter class telescope like the TMT. And I want to focus on that to close. This is the TMT. We still don't know exactly where it's going to be put. I hope it's going to be put on Maunakea. And if you've been following this issue in the last year, you may have seen images like this. People who feel like they've been ignored for a long time, they're raising their voice. And that's good. It is also important, though, to hear the voices of the majority of people who live in Hawaii, including at least half of the Hawaiian population who support the project. Their voices matter too. And when we listen to them, the science that really drives them, that they see as insightful, that they're passionate about, is imaging planets around a nearby star, even imaging an Earth. So what happens if we take SCEX-AO and put it on TMT? We probably won't get better contrast than we will get in the next couple of years, where we think we'll be able to get 10 to the minus 8 contrast. But we'll be able to do that at smaller angular separations. And that puts things like an Earth-like planet within striking distance. This shows a simulation of the kind of contrast we need in order to image planets around the nearest low-mass stars, the kinds of planets that are outside of the reach from upcoming NASA missions like WFIRST and maybe even HabEx or LUVOIR. If we take the contrast curve we think we might get with SCEX-AO and TMT, these are within striking distance. So it is entirely possible, is my hope, that within the next decade or two, we will be able to image another Earth from the highest, at least viewed from the base place on this Earth. I'd be happy to take any questions you have.
Okay, and I'm going to be talking about something that makes use of actually very classical observing techniques, but in the ultraviolet. And this is, we have found infalling bodies, and we're starting to get a handle on their composition around a southern A star, so something with a white light spectrum, and there will not be a quiz on the HD number for this thing. So the technique that we've been using is absorption spectroscopy, and that is misspelled, oh well, using HSD STIS and CAUS, two data sets using both cameras or both spectrographs separated by almost 6 days. What we've seen is absorption features reaching velocities as high as 160 kilometers per second in ions of silicon and carbon, and they are visible throughout each of our two sets of spectra, and they also have some distinctive features to them. The profiles and variability are similar to what has been previously seen for the last 30 years in the spectra of Beta Pictoris, the brightest member of one of the nearby young moving groups of stars. And it is also very similar to what is expected to be seen for sun-grazing comets if you have enough material associated with them. Well, this keeps on jumping. Okay, and in the case of these are models for Beta Pictoris in the upper right. And what you can see is something that's sort of doing a star-grazing orbit that passes in the line of sight between you and the star. You get an absorption feature which moves with time. The highest velocity portions of the feature mark where a body is. The lower velocity stuff sort of trailing behind it is actually the tail of what we think are things that look remarkably like Kreutz family comets in our own solar system. So this is a case of, going a ways away to see something that is actually rather familiar to people who have been studying the sky with SOHO. SOHO has found more than 2,000 of these things. And the thing is, when you get a good comet near the sun is the little white circle in the lower right image. When you get something that close to the sun, it's bright and it's large. So you have a good chance of seeing a significant amount of absorption in the line of sight as the body transits in front of the star. Now, what we have some significant differences from the kind of activity that has been seen in Beta Pictoris and also in our solar system. In the case of Beta Pictoris, you're looking actually edge-on to the disk of surrounding the dust disk surrounding the star, and so you get some gas features, molecular gas features, due to CO, which we do not see in this system. And you also, in the case of Beta Pictoris, because of the viewing geometry, you see a very stable absorption component as well as the higher velocity stuff that varies on timescales of hours. And the difference may be both how we view the system. We're not precisely edge on to the system. We're about 75 degrees from the polar axis. And the fact that this system, when studied with Herschel, seemed to have no cold dust component. So what we think we're looking at is this is artwork that was generated for a press release 2 years ago by the European Southern Observatory. And what they see is material associated with 2 families of comets with slightly different orbital properties. And the thing that you notice is in their concept, they said, oh, we've got multiple objects, something like Shoemaker-Levy 9. And you can tell that if you have an abnormally long transit. So if you can say, okay, at this velocity, I expect this stuff to clear the stellar disk in maybe an hour, and it just keeps on going on and on and on, the inference is your comet has friends. And so it's somewhat difficult to say how many events that you have, but it certainly tells you that there's a lot going on. The other thing that is important is to get comets or planetesimals into these star-grazing orbits. You need a massive body to basically pump up the eccentricity of these bodies, and you're typically sampling objects that are in a mean motion resonance with the planet. Now, we haven't seen the planet in this system, but we think one is probably here. And so this becomes then a technique for saying how many systems have a high probability of having a Jupiter mass planet, probably located at distances from the star, which are, if not accessible to the new generation of extreme AO imagers, certainly to the next generation of such imagers. And so if you do this for enough stars in one of these moving groups that all have the same general stellar properties, you can start to say how common are Jovian mass planets. And what we can say is that in the Beta Pictoris moving group, at a rather well-dated age of 24 plus or minus 1 million years, there are 5, count them 5, stars of A spectral type and 3 early F stars. Of these 8 stars, 2 have detected planets, 2 have the transiting exocomets. So this implies that we're approaching 40% for detected things. Now, we can't do this except when we have a rapidly rotating star and we're viewing it close to its disk. So this is a lower bound to this kind of activity in these systems. And the thing that is interesting is that when people have done larger surveys of various moving groups, they have found that the planet frequency is much lower, 2% or so. So this suggests that there are certain classes of stars that may be very favorable hunting grounds for Jovian mass planets, and the next things that people will want to be able to do is to go find them using instrumentation like Thayne and Tyler have been working on. So again, I'm happy to take any questions, and thank you very much.
All right, thank you all very much for your presentations. We'll go to Q&A now, and we'll start here in the room. Please remember to raise your hand, then wait for the mic, and Larry will bring it to you. Tell us your name and affiliation and who your question is for, and if you're on the webcast and you want to ask a question, please enter your question into the text chat. All right, we'll start down here with Maunakea.
Hi, I'm Monica Young with Sky and Telescope. Tyler, I was hoping, I know that they're preliminary data, but can you tell us anything about the spectra that you got from the planets around HR 8799?
Do I need to push the button?
No, you don't.
Oh, okay. Yeah, so they're looking really, really promising. You know, so we're working on calibrations right now mostly, which is my major caveat. But the signal and noise on those spectra are just phenomenal so far. And
Detections of spectral lines?
detections of spectral lines, we haven't tried to fit to the models yet. Yeah, that's right. So, but it's a work in progress really. So we just started getting this data, and what we really want to do is start fitting to the higher resolution modes as well. What I featured here was the broadband mode, but what we've actually done is imaged HR 8799 in all 4 modes. And so I was just being selective about what we talked about today.
Okay, more questions? All right, one down here in the front.
Hi, Zui Nguyen, University of Virginia. My question is for Ms. Girma with the Spitballs. I was just wondering, considering that 90% of these Spitballs are being ejected from our galaxy, do you believe that perhaps the ones that do stay within our galaxy have a chance to be captured by other star systems and actually become part of binary systems with other stars?
Yeah, I don't think there's anything that could go against that notion. So.
Do we have some questions? Oh, we got one more here in the room. Ethan?
Hi, this is Ethan Siegel from Starts With a Bang at Forbes. This question is also for Eden. I'd like to know, based on the statistics you found and the rate at which you expect these stars to be torn apart and create these spitballs along with the velocity distribution, here at Earth, if we go to look for them, what are the relative populations that we'll be likely to see at the current point in time? Will we be more likely to see the fast-moving ones that are perhaps rarer because most of them are gone, or will we be more likely to see the slower-moving ones that are probably going to be harder to distinguish from the other 99.9% of rogue planets?
Well, actually, a huge thing about these fragments is that they are, what will make them extremely distinguishable from normal planets is how fast they're moving. So even the slowest fragments will be moving around 1,000 kilometers per second, whereas normal planets sort of move around like the 10 kilometers per second range. So, however, yeah, so this velocity difference makes it potentially easier to detect through microlensing, and I'd estimate if we use microlensing as a tool, by the rate of occurrence, maybe we could see a couple per year.
And with which piece of equipment is that?
So you would be able to use something like the LSST.
So not with current technology?
Yeah.
Thank
Yeah.
you.
Do we have some questions online? Oh, well, then we can spend a little bit more time in here. Any more questions down here? We got one over here. Oh, here we go, over here. John? Everybody's as far from Larry as they can get. Makes it inconvenient.
Hi, John Wenz with Astronomy Magazine, and this question is from Ms. Girma, too. What's the, I guess, eventual fate of these spitballs? Does the gas stay kind of gravitationally bound, or does it kind of eventually become more and more diffuse?
So I think they do stay clumped together. They do stay these concrete objects. But to fully understand this better, we would have to use some sort of more extensive simulation to be able to look more in depth into that cooling process, that traveling process. So.
Thank you.
Come back to Monica. Larry, come back to Monica down here in the front.
Yeah, Monica Young again. Yeah, just to follow up on that, I was curious, do you have any estimates on how much mass is contained within both the bound and the unbound populations?
Yeah, from the work that Eric Coughlin did in his simulations, he saw that these fragments were on the range of a Jupiter to 2 Jupiter masses.
So I mean like total mass, like how many
Oh, how many
of these
fragments
objects are out there?
totally?
How much mass is there
Oh,
total?
yeah, so that I would estimate to be around 100 million.
100 million Jupiter masses, or
Yeah.
100 million objects, you mean? Okay.
Yeah.
Okay.
Any other questions? Okay, Martin.
Martin Ratcliffe, freelance for Thayne. What determines the youngness of your youngest disk?
Okay, so we have a catalog of the debris disk we've been able to resolve around nearby stars, for example, with Hubble, with the Gemini Planet Imager, with Sphere, with other instruments. And depending on what you count as a debris disk or not, the youngest debris disk we've been able to resolve is either 5 million years old or 8 million years old. This star, if we actually look at where it is on the sky, it's in the constellation Taurus, is slightly foreground to the Taurus Auriga molecular cloud, which is this archetypical laboratory for studying the earliest stages of planet formation. If we look at its space motions, what we actually see is that it looks like it's part of this bubble of star formation that preceded Taurus Auriga. Is actually located in what is called the Maunakea 17 Association, named in honor of the deputy director now, I think, at JPL, who's my good friend Eric Maunakea, who is here. So he actually helped me on that. The estimated age for that is somewhere between about 3 to 10 million years. So that is why we think it is possibly the youngest debris disk ever imaged and a critical probe of the earliest stages of Kuiper belt evolution. And it's also an object we're pretty sure has a planet somewhere. And if we get better data with SkexAO, which is going to be easy to do, we might be able to image this planet.
Any further questions here in the room before I unleash my barrage? I always have a few questions. All right, my first one's for Eden and James to sort of argue over. Let me think about it. So I start with Eden. You mentioned in response to one of Monica's questions that the mass range of these spitballs, which essentially become rogue planets, is in the neighborhood of 1 to 2 Jupiters. But how firm is that range? Is it 1 to 2 Jupiters plus or minus a Jupiter or two, or is it pretty constrained? So basically, what is the product that you get from these tidal disruptions and then these recollapses? And where I'm leading with it is, could you have something that is significantly less massive? And also, what are the error bars on your estimate of 200 parsecs? How likely is it that there might be something way closer, which then leads to what James was talking about, which is, maybe we've captured a rogue. What is the statistical likelihood or the slim possibility that we've captured a spitball?
Oh, that would be cool. That's not an argument. That's more like a collaboration. So the first question on the masses. So that figure comes from the simulations that Coughlin did back in 2015. And from that literature, it did seem that it was pretty constrained. So, and then what was the next thing on?
Well, it was the distance range.
The distance range.
You said it.
Yeah.
You said a minimum of 200, but is it a minimum of 200 plus or minus 100 or plus or minus 200? I mean,
yeah.
How close could something actually be?
Yeah. So that estimation was definitely dependent on the statistical data that I had received from my own simulations. And the integration that I used through Mathematica, since Mathematica is sort of the order of precision is it's essentially infinite. I don't know, but infinite doesn't sound right. But it is like a very, very powerful integrating machine. So I definitely want to put it out as this is like an estimate, and like you shouldn't be thinking like, oh, it's exactly 200 parsecs. There's definitely room for variability in that distance. I wouldn't be able to say what the actual bounds are, but actually, from the specific number that I calculated from my data, it was 212.9. So I think, though, it is pretty likely, especially because we don't necessarily have to consider these fragments being created from simply our own galaxy, but we could also consider fragments that are sort of being rained down upon us from other galaxies around us. Because if there's a tidal disruption happening in our black hole, and there are tons of supermassive black holes around us, we can consider the same process happening elsewhere. So, yeah, there really is a lot of variables and a lot of chance for these things to be close to us. So I don't know, James, do you want to pick it up from there?
Well, I mean, with the masses, it sounds like it's definitely plausible with it, because the masses I were using range anywhere from 3 times the mass of Earth to 10 times the mass of Jupiter, and the masses of your fragments are within that bound. So I mean, it's plausible that something like that could be picked up into our system.
So let me follow up by asking if in your simulations, your dynamical simulations where you're throwing all these rogues into a solar system, now that you've seen Eden's result, is there anything you can do in your simulations to go back and play with it and try to determine, what might the likelihood be that that one of these rogues has, come in from some other part of the galaxy rather than just passing, coming from a nearby star system or something?
Well, with things like that are that massive, typically, as I was saying earlier, it would really disrupt the inner the inner dynamics of the inner solar system. So, because our solar system is as tightly packed and organized as it is, we haven't seen anything larger than Neptune, at least so far. It doesn't seem likely anyway. Mm-hmm. So that kind of limits the possibility of something like that having happened way down.
Well, Planet 9, as I recall, is in the neighborhood of Neptune mass, if it exists at all. So, right? So it could have, if Planet 9 were a captured rogue, it wouldn't, according to your simulations, it probably wouldn't have disrupted the solar system.
That's correct.
Okay. So now I have a quick question for Thayne and Tyler. In fact, Thayne, you just mentioned the Gemini Planet Imager. Now, you were saying that SCEX-AO is the first dedicated planet imager on Maunakea. Well, where's the Gemini Planet Imager? Is it in the southern hemisphere, or what's going on there? I thought that was also a dedicated planet imager.
Yes. So the Gemini Planet Imager is in Cerro Pachon, just outside of La Serena, Chile, in the northern, in the Andes mountain chain. Cerro Pachon is not as good of a site for for exoplanet imaging as Maunakea, not even close. If you take the metrics by which you are able to estimate the ability of a given system to image planets, one of the typical parameters is what's called the coherence time of the atmosphere. It's the sort of measure of how turbulent that atmosphere is. The coherence time for Maunakea is far longer, is far less turbulent than it is on Cerro Pachon. And this matters. And I also think this matters for the future. Could we do the same science from the alternate site at TMT? I think the simple answer is it would be harder. My intuition is no. And the reason is because the coherence time in the Canary Islands is shorter. Also, the water vapor level is significantly higher. That substantially impacts your ability to be able to resolve biomarkers, for example, oxygen, that we could actually see with one of these systems. And actually, one of the plans for the Gemini Planet Imager is to move to Maunakea at Gemini North. And a lot of people are very excited about that, including me.
Okay, and then for Tyler, you mentioned a couple times this parameter called inner working angle, but I don't recall you defining it, but I'm imagining you just talking about how close you can get to the central star, or is it something else?
Yeah, that's right. It's how close you can actually detect to the star. And so that's a fundamental parameter of most coronagraphs, and actually even the wavefront control algorithms that we use to correct the starlight and the residual aberrations that Thayne was just referencing. So the idea behind that low resolution mode that we put in for Charis is that what the star looks like is completely dependent on your aperture. And as you look, and the wavelength that you're observing at, and the longer the wavelength, the bigger the image of the star appears to be. So when you have a longer bandpass, the star and the errors in the image of the star that wash out the planets are scaling and moving more. And we can use that fact that the star and the speckles or the errors in that image are moving a lot, but the planets are not, or the disks are not moving, to actually post-process and figure out what in the image is a planet, what in the image is a star. And the more bandpass you have, and the more those move, and the closer you can get to the star, which is incredibly important for trying to detect these things.
Now, a lot of us are looking forward to the TESS mission coming up, which is going to discover presumably a lot of transiting exoplanets that are around relatively bright stars. Will you be able to follow up some of those systems with your system and try to image some of these exoplanet systems, or are they going to, on average, be too far away or not quite bright enough or too bright, or, you know?
Well, in terms of actually imaging close-in transiting planets, no. We just simply don't have a large enough telescope. But one thing we can potentially do is that we can potentially look for slightly more distant companions to the transiting planets detected with TESS. Additionally, what we would like to do is a large campaign combining Skexia with a dedicated precision radial velocity instrument. And so you could think of, you switch back and forth between those two, you follow up TESS objects with both methods.
And then a question for Carol. You were mentioning that you don't see carbon monoxide in the spectrum, right? So is that implying that these are like less cometary and more asteroidal? Could you be seeing broken up rubble piles, or is it something, what is that really implying?
Well, in the case of Beta Pictoris, the carbon monoxide absorption, it almost imaged the system. And they find that the carbon monoxide emission is largely confined to the outer planetesimal belt, and it has a clumpy structure. CO does not last long in the radiation field of a star like Beta Pictoris. So typically, you're seeing stuff that was released from the solid phase within the last 150 years. Yeah. And the other thing is that we've actually got the spectra for 3 of these systems now. And in the case of 49 Ceti, another system with CO in the outer planetesimal belt, our line of sight to the star just misses that outer planetesimal belt. So when you're using absorption line spectroscopy in the UV, you only see it if it's between you and the star. And so we can say, yeah, that system definitely has CO, but it's not in the line of sight. In the case of the star I presented today, we think it may not have CO because it may not have an outer planetesimal belt. It has a distant binary companion, and it's possible that somebody sideswiped the system at some point in its youth, and the Kuiper belt analog is gone.
So it's not really saying anything specifically about the comets.
Well,
it's about the
right,
rest of the environment in the
it's more about the outer
system.
part of the system. The comets actually look very similar to Beta Pictoris. And so it's entirely possible that what we are looking at is icy asteroids, rather than what we would think of classically as comets in our system. So, I mean, one of the things that we want to be able to do is to build up a large enough data set that we can start to do disk tomography and say, this system has these components. We see this, we don't see that.
Okay.
And then start to say where things are coming from, what their orbital properties are, and stuff like that. So, I mean, when I went to graduate school, none of this science existed. And no one had any concept that we were ever going to be talking about minor bodies in somebody else's planetary system.
Yeah, it's pretty remarkable. Any other questions here in the room? Anything else percolated up online? No? Okay. Well, in that case, we'll bring it to a close. It's just about been an hour anyway. I want to thank you again for your presentations and thank you for your attention. We have 2 briefings tomorrow, the last day of the meeting. In the morning, we have one on black holes, green galaxies, old stars, and new stars. And then in the afternoon, we will be doing a seminar for science writers on this year's, used to be next year's, but now it's this year's, big solar eclipse across America. See you tomorrow. Thanks a lot.